This video is about the decision tree operator. This operator builds classification models to allow a label attribute to be predicted from a set of regular attributes. So we'll cover a basic overview of the operator to build a model, and we'll look at certain of the parameters. I've listed them there. We'll also look at the types of problem which this operator can be applied to, some of its strengths and weaknesses, and we'll actually also use the apply operator to show the model being used to make a prediction. Let's start with a process. So this process, it contains a subprocess to make some data. The details don't matter. There are two outputs. The top output is some training data, which is passed to the decision tree operator where a model is built, and that's sent to the apply model operator. In addition, the example set corresponding to the training is sent to the output of the whole process, so we can look at it at the end. The second output from the make data is some test data, i.e. data with no label. We don't know what the answer is. We're hoping the apply model operator will tell us. So I've split that in two by using the multiply operator, passing one copy to apply model and the other copy just to the output so that we can look at it all in one place. So if I run that, we will get 4 tabs. So this is the unseen data. But if we look at the original input, this is the training data. It's 149 examples, and you can recognize it's the IRIS data set with attributes A3 and A4 only included. And I'm basically going to try and predict what ID 79 of that is with A3 at 4.5 and A4 at 1.5. You can look it up yourself, but let's not spoil the ending, and when we click on this tab here, we'll see the answer. If we look at the input data, if I plot an advanced chart view of that, you can see A3 as a function of A4. We can see the coloured points are different labels, so there are 3 basic groupings. So the idea is that we're going to try and predict where, if I remember the data, A3 at 4.5 and A4 at 1.5. So 4.5, 1.5, it's about there. So there's a good chance it's going to be Iris versicolor, but it's quite close to the Iris virginica. So it's not a done deal by any chance. Okay, let's go back to, so let's look at the decision tree. This is the decision tree that's been built from that training data. I'll zoom in. So let's interpret this quickly. What this is saying is, you start at the top and you say, right, look at A3 first. If it's less than or equal to 2.45, then you know of the 149 it's seen. We can be 100% certain, as you can see from the pop-up, that it's Iris setosa. If on the other hand it's greater than 2.55, then you need to go to A4 attribute and do another comparison against 1.75, or if it's greater than that you have Iris virginica, or less than, you do a bit more drilling into the tree. There is a description, a text description here, which you can cut and paste, and sometimes I find it useful actually to visualize that on the graph. So let's remember A3 2.45. So what you can do here, you can insert a line, a vertical line, because it's A3 2.45. So basically what the decision tree is doing, it's finding the best place either along the A3 or the A4 axis to split the data. And the way it does it is to use various mathematical approaches, which we'll look at shortly, and we can go on doing this. If I go back to the decision tree, I want to do A4 less than equal 1.75. So I go back to here, add another line. It's a horizontal line this time, and it's 1.75. And you can see, yeah, okay, it's done quite a good job. So it's essentially found the optimal place on the A4 attribute that will split the attributes into 2 groups. And basically what it's doing is using an entropy measure to try and find the purest split point I'm not going to go into any great detail about this because it'll detract from the overall message, and of course that may well be the subject of a later video. Anyway, I could go on going down the tree, drawing more and more lines, and eventually we'd run out and hopefully would have found a home for every single one of the examples on this picture. Anyway, the next thing to do, let's now see if the model predicted what we expected. We're expecting Ares versicolor. Let's look at the example set here. Sure enough, so this is the prediction that the model has made. It's basically saying that A3, A4, these values, the prediction is Ares versicolor. It's also giving a confidence about how good it thinks that is. And the fact that it's not 1 for Ares versicolor rather implies it's getting quite close to the Virginica sort of clustering. So anyway, the model works, yes. So our human intuition about it working is great, it's worked. So you might say to yourself, so what? Job done? Unfortunately, of course, it's not as simple as that. Let's go back to the design view and let's have a think about what's going on. So a great part of data mining is getting the models built correctly so that they predict with the smallest error without overfitting the data. And there's a huge amount of work implied in those last two sentences. So, and generally what you have to do is spend time getting the various parameters, in this case to the decision tree operator, correct for the data you have. Now that's going to be the subject of later videos for things like cross-validation, but for now let's just briefly look at the decision tree operator and what the effect of changing some of these parameters is. So, first thing, there are various criteria here. Now these really dictate the mathematical algorithm used to decide where to draw the lines, in our example on the A3 and A4 axes. Now in general, when there's multiple attributes it gets very complicated to visualize, and I'm not going to go into any detail here, but information gain is essentially a measure of entropy. Gain ratio is similar but does a better job when there are lots of different possible values, particularly in the situation where attributes have nominal values, lots of nominal values. Gini index is similar to entropy, but then obviously subtly different formulas used and accuracies to do with prediction accuracy. Details don't matter too much, and in general you'll always have to spend time deciding which one of these you want to use. I've just picked Gini index for this illustration. Now these ones, minimal size for split. Let's work down these one by one, and what we'll do, we'll change these and we'll see what happens to the tree that's created. So minimal size for split, this is essentially saying if a node that you're considering is less than 4, then it won't be considered for splitting. So if I increase that to 100, let's see what happens. So there's the decision tree. So that's exactly right, because we know that the original example set had 149 examples in it. If I hover here, you'll see subtree size 149. So the minimal size for split 100. Well, that's okay. We're greater than 100, so we can split this, which is what's happened. Now, you can see now that 99 in this one, 50 in this one. So 100 is too big. So essentially, this means it stops at this point. If I go back to the design view, if I change that to be just 98 now, we should find that the tree gets a bit more complicated, because, yep, sure enough, that node there, that has 99 elements in it, so that's more than 98, so this can be split, which is what happens. So generally speaking, as you make the minimal size for split larger, the tree gets simpler. Now, in general that's a good thing, but the trouble is if it's too simple it's no good, so the balance is to get it just the right size to make the predictions you want. I'm going to put that back to 4. Minimal leaf size, so this is saying that leaves, the final results must be greater than this in size. If I put that down to 1, and let's set this minimal down to 2, Let's see if we can persuade the thing to get more complicated. Well, sort of. If I put my mouse over that one, okay, there's one element in that, so the leaves have gone down to size 1, which is essentially made the tree much more complicated. And that may be a bad thing because it's now it's hard-coded a route through, so you may decide, well, actually that's a little bit too closely fitted to the data, so it may not do a good general job when it comes to unseen data. So the basic rule is, as you make that smaller, the trees get more complicated. So the minimal gain parameter, this really applies to the information gain and gain ratio options here. So if I set that to information gain, let's run this, see what the tree looks like. We see, okay, nice looking tree. If I increase this, we'll see that the tree gets simpler. I'll explain that in a moment. Yep, sure enough, the tree's got a bit simpler. What's happening is that it's comparing a before and after, before a split and after a split, and essentially the entropy before the split is measured as it is after, and the difference is calculated. And if the difference is less than this minimal gain, then the split is not allowed. So what that means is eventually it will run out of splits it can do, and it will just give up and say, right, that's it, the tree is done. Anyway, the basic point is, as your minimal gain parameter is increased, the tree gets simpler. Obviously, if you increase it too much, so something like 1, whatever that might mean, then you'll get the world's simplest tree, which is a single stump. So generally speaking, the activity really is to tune that. Maximal depth is the final one I'll look at in detail. Maximal depth basically dictates how deep the tree is. 20 means 20 layers. If I put that to 2, the tree will stop growing when it reaches 2 deep, i.e. a bottom level and some leaves. So that's 2. If I put that to 3, we should see it get a bit more complicated. Sure enough, 3, and so on. So again, the bigger that number is, the more complicated the tree, and the risk is that it's not a general tree. But obviously, if the tree's too small, it's not good enough. It won't be able to generalize at all, to underfit the data. So the final parameter, there are some other parameters here. In my experience, these pre-pruning ones, you generally leave those alone. If you turn no pre-pruning and pruning off like that, you tend to get a very complicated tree indeed, potentially. I don't think it'll work with this data. Let's see if it does. Maybe, yeah, it looks like it's got a bit more complicated. If I turn pruning and no pre-pruning off. Yeah, okay, so pre-pruning has, I happen to know in my experience, pre-pruning is the key one to do there. And basically it does, well, to use the gardening analogy, it picks off things it doesn't think are going to make a good tree, and it's generally advisable to always pre-prune. And you can change these numbers here to tune that. In my experience, I've never really seen that make that much difference. The general point is turn pre-pruning on, is my advice, i.e. leave the default as it is. So, final thing to look at is, what is the decision tree operator good for? Well, generally speaking, let's just run the data, let's have a look at it here. So, it can only cope with this particular operator can only cope with nominal labels, and obviously it can cope with numeric or in fact nominal attributes here, these regular attributes. As we saw, the decision tree model is very easy to visualize and understand, and computationally it's relatively quick compared to others, and it does a reasonably good job compared to others. In the literature, that apparently the pre-pruning allows the thing to be immune to noise, and I also read in the literature that correlated attributes don't tend to have too much of a detrimental effect on it. The algorithm is greedy, i.e. it's locally optimal, and will tend to take decisions about a single attribute rather than generally thinking actually what's the big picture here. So there's a risk it may not find the best global solution. Also subtrees, sometimes you can get, particularly for large data sets, you can sometimes get the same subtree replicated time and time again. So it can sometimes make the tree tricky to understand. And there are a certain class of problems it can't cope with, the so-called parity problem. This is where I think a label is true if there's an even number of binomial trues and falses in the input data. So an even number of trues leads to true, if an odd number of trues leads to false. That's a parity. So it can't really cope with that. Neural net would probably be better in that situation. So, but anyway, the bottom line is everyone uses it, and it's worth trying it because it's very easy to understand, and if nothing else, it helps you understand your data, even if it may not produce the best model. And of course, as I mentioned before, in general, you do have to spend time tuning these parameters here, which we'll cover in later videos, and those will be essentially about cross-validation and perhaps some of the loop operators to try and get these parameters set right. So what I'll do is I'll run this one more time, and we'll just bring up the decision tree and the input and output data set. So here's the input data, here's the tree, here's the test data, and finally the result.